The two hemispheres formed under different conditions. The near side faced Earth, experiencing tidal forces that may have affected its internal structure. The far side faced deep space, exposed to more intense radiation and micrometeorite bombardment. The near side received Carib-enriched materials from the Procellarum region. The far side did not. These differences accumulated over billions of years. Small initial variations became amplified through feedback processes. More heat led to more volcanism, which led to thinner crust, which led to more volcanism. Less heat led to less volcanism, which led to thicker crust, which led to less volcanism. The two hemispheres diverged, each following its own evolutionary path. The South Pole Aitken Basin sits at the intersection of these divergent histories. It formed during the final stages of magma ocean crystallization, a time when the lunar interior was still partially molten and compositionally stratified. The impact excavated materials from multiple depths, mixing them in ways that created unique compositions. It redistributed heat-producing elements, altered crustal thickness patterns, and created structural weaknesses that would influence volcanism for over 1 billion years. And beneath it all lies that mysterious mass anomaly, metallic remnants of an ancient asteroid. Dense mantle cumulates churned up by the impact, some combination of both. The gravity data alone can't answer that question. We need more information. Seismic data would help. Placing seismometers around the basin and recording moonquakes could reveal the anomaly's internal structure. Electromagnetic sounding could distinguish metallic conductors from silicate rock. Sample return from multiple locations within the basin could constrain composition and formation processes. The Artemis missions will provide some of these answers. Proposed landing sites sit on the basin's rim, on the thorium-rich ejecta deposits. Astronauts will collect samples, deploy instruments, and conduct field observations that robotic missions cannot replicate. They'll walk on terrain thrown from the deep lunar interior 4.25 billion years ago. They'll gather rocks that preserve evidence of the collision that created the solar system's largest known impact crater. But even Artemis won't solve all the mysteries. The basin is too large, too complex, too deeply modified by subsequent processes. Each sample will answer some questions while raising others. Each measurement will constrain some parameters while revealing new anomalies. This is how planetary science works. Understanding builds slowly, accumulating piece by piece. The far side is patient. It has waited 4.5 billion years to tell its story. A few more decades won't matter, but while we wait for future missions to fill in the gaps, the far side continues revealing surprises through what we've already observed. The Artemis II flyby in April 2026 provided something no robotic probe could deliver. Human eyes witnessing the entire lunar far side for the first time in history. Christina Koch, Victor Glover, Reed Wiseman, and Jeremy Hansen spent 7 hours photographing and documenting surface features. They saw things that challenged their expectations. Koch described smaller impact craters glowing like a lampshade with pinprick holes, far brighter than the surrounding terrain. The crew reported brown and green hues on portions of the near side, colours that defied their mental image of a monochrome moon. These weren't hallucinations or instrument artifacts. Human vision perceives subtle colour variations that cameras often miss or flatten. The astronauts saw the moon as it truly appears, not filtered through sensor limitations or image processing algorithms. Their observations complement, but don't replace robotic data. They add a layer of context that pure measurement cannot capture. The Artemis II crew also experienced something unprecedented, a solar eclipse viewed from behind the moon. For 1 hour, they watched Earth block the sun while orbiting the far side. Totality revealed Mars, Venus, and Saturn alongside background stars. The sun's corona appeared as delicate wisps, baby hairs they called them, fringing the lunar disk. This unique vantage point drove home the moon's true isolation. During the eclipse, with Earth blocking the sun and the crew positioned on the far side, they were as far from home as any humans have ever traveled. They set a distance record, 252,756 miles from Earth, over 4,100 miles farther than Apollo 13's emergency trajectory in 1970. The emotional impact was profound. Koch reflected that seeing Earth from this perspective revealed how much we share, how Earth provides everything we need, how that realization can't be fully grasped until you've experienced the alternative. The far side offers that alternative. It's a place utterly unlike anywhere humans evolved to live. Space weathering shapes the two hemispheres differently. The far side receives stronger solar wind radiation because it never enters Earth's magnetotail. During each lunar month, the near side spends time shielded by Earth's magnetic field. The far side does not. This exposure leaves distinct signatures. Chang'e 6 samples show the effects. Compared to near-side materials, far-side regolith lacks vapor deposition layers. It exhibits thinner amorphized rims on individual grains. Solar flare track densities are lower. Nanophase metallic iron particles are less numerous but larger on average. These differences accumulate over billions of years. Why does this matter? Space weathering affects how we interpret remote sensing data. Spectroscopic measurements from orbit detect weathering products, not pristine compositions. Understanding the differences between near-side and far-side weathering helps us correct for these effects. It improves our ability to infer what lies beneath the regolith without drilling. The far side also offers unique opportunities for radio astronomy. Earth's electromagnetic noise, radio, television, cellular signals, everything electronic, creates constant interference for radio telescopes on Earth's surface. The moon's far side provides natural shielding. Place a radio telescope there and Earth's noise vanishes completely. Low-frequency radio waves blocked by Earth's ionosphere could be detected from the lunar far side. These frequencies carry information about cosmic dawn, the epoch when the first stars ignited and ended the universe's dark ages. They reveal processes from the early universe that higher frequencies cannot access. China's Chang'e 4 lander, which touched down on the far side in January 2019, carried a low-frequency radio spectrograph. The Yutu-2 rover continues operating after more than 5 years, making it the longest-lived lunar rover in history. It demonstrated that sustained far-side operations are feasible with relay satellite support. The Queqiao relay satellite, launched in 2018, made Chang'e 4 possible. Positioned at the Earth-Moon L2 Lagrange point, it maintains line of sight with both Earth and the lunar far side. All communications pass through Queqiao. Without it, the lander and rover would be deaf and mute, cut off from ground control. This communication challenge defined early far-side exploration. During Apollo missions, spacecraft passing behind the moon entered communications blackout. Astronauts were truly alone, beyond Earth's reach, dependent entirely on their training and systems. No one could help if something went wrong during those tense minutes. Harrison Schmitt, the geologist astronaut who walked on the moon during Apollo 17, lobbied hard for a far-side landing. He wanted to explore Tsiolkovsky Crater, a lava-filled impact basin on the far side. His proposal included a dedicated relay satellite at L2. NASA rejected the plan. Too risky, too expensive, insufficient return on investment given Apollo's limited remaining flights. Schmidt's vision waited nearly 50 years to become reality. Chang'e 4 fulfilled it, demonstrating that far-side landings are operationally feasible. Artemis will expand on that foundation. Proposed landing sites sit on the rim of South Pole Aitken Basin, on thorium-rich ejecta deposits that tell the story of the impact. Future missions will target specific questions. Chang'e 7, scheduled for 2026, will survey for water ice near the South Pole. Water ice in permanently shadowed craters could support human exploration. It provides drinking water, oxygen for breathing, hydrogen, and oxygen for rocket fuel. Finding accessible ice deposits changes the economics of lunar operations. Chang'e 8, planned for 2028, will test in situ resource utilization technologies. Can we extract oxygen from lunar regolith? Can we manufacture building materials from local resources? Can we operate mining equipment remotely with Earth-Moon communication delays? These aren't academic questions. They determine whether sustained lunar presence is feasible. The far side factors into these plans because it represents half the Moon's surface and resources. Limiting exploration to the near side means ignoring vast territories. The far side's thicker crust may contain mineral deposits absent from the near side. Its reduced volcanic resurfacing preserves ancient terrains that near side Maria buried. Its unique exposure to space weathering creates different regolith characteristics that might prove valuable, but practical considerations compete with scientific ones. Communication requires relay satellites. Landing sites must balance scientific value against operational constraints. Solar power is limited near the poles where permanently shadowed craters exist, alongside peaks of eternal light. Nuclear power becomes more attractive for far-side operations, especially for facilities that need consistent power regardless of sun angle. The far side's isolation also offers advantages. Radio telescopes operate without interference. Seismometer networks detect moonquakes without contamination from human activity. Astronomy conducted from the far side achieves sensitivities impossible on Earth, or even on the near side. The Moon becomes a platform for observing the universe. These future possibilities rest on understanding what's already there. The South Pole Aitken Basin anchors that understanding. Its age, 4.25 billion years, precisely determined from Chang'e 6 samples, provides a calibration point for the entire lunar chronology. Impact basins across the solar system can now be dated relative to this anchor. The basin's composition reveals the Moon's internal structure. That mysterious mass anomaly beneath the basin floor constrains models of the lunar interior. Is the Moon's mantle homogeneous or layered? How much metal segregated into a core? What happened to dense materials that should have sunk during magma ocean crystallization? The basin's volcanic history extends our understanding of lunar thermal evolution. Volcanism occurred in South Pole Aitken Basin from at least 4.2 billion years ago until 2.8 billion years ago, possibly later. That's over 1.4 billion years of intermittent volcanic activity. What kept the interior molten for so long? Where did the magma come from? Why did it eventually stop? The basin's impact trajectory, now recognized as southward rather than northward, changes how we interpret its structure. Ejecta deposits concentrate southwest of the basin. The thorium-rich signature there suggests excavation of late-stage magma ocean materials. The gradual topographic transition toward the south indicates an oblique impact angle, possibly as shallow as 30 degrees. This oblique impact scenario explains several puzzles. It accounts for why the basin didn't excavate deep mantle materials despite its enormous size. It explains the asymmetric distribution of ejecta. It reconciles the observed crustal thickness, about 30 kilometers beneath the basin floor, with impact models that predicted near total crustal removal. Yet questions remain. If the impactor struck at a shallow angle, where did it come from? orbital mechanics constrain possible trajectories. The timing, during late magma ocean crystallization, narrows the possibilities further. The solar system at 4.25 billion years ago was still chaotic, with planetesimals scattered throughout the inner solar system. Any of thousands of objects could have struck the moon. We'll never identify the specific impactor. It vaporized on contact, its atoms mixing with lunar material in the impact plume. But we can characterize it. Size estimates suggest roughly 200 kilometers diameter. Composition was probably chondritic, similar to asteroids. Velocity was lower than typical impacts, consistent with an object in a similar orbit to the moon. The energy released was staggering, 1 trillion times greater than an atomic bomb explosion. For comparison, the Chicxulub impact that killed the dinosaurs released about 100 million megatons. The South Pole Aitken impact released energy equivalent to roughly 100 billion megatons. The moon rang like a bell for months afterward. That energy didn't just create a crater, it reset the moon's thermal state in the impact region. Rock melted to depths of dozens of kilometers. The melt sheet took millions of years to solidify. As it cooled, minerals crystallized in sequence, creating layered rocks that preserve the chemical evolution of the cooling magma. Chang'e 6 returned norite samples crystallized from this impact melt. Their composition differs from norites collected on the near side. They contain highly anorthitic plagioclase, rare earth element pore compared to typical lunar rocks. They're rich in magnesium-bearing pyroxene, abundant iron-nickel metal particles with meteoritic nickel-to-cobalt ratios dot the samples. These characteristics point to impact origin. The metal particles came from the impactor. The plagioclase composition reflects rapid crystallization from superheated melt. The rare earth depletion indicates minimal contamination from creep-rich materials. The South Pole Aitken impact created a massive magma chamber that evolved independently from the near side's volcanic systems. Variable grain sizes and cooling rates within the norite samples reveal complex thermal histories. Some portions cooled quickly near the melt sheet's surface. Others cooled slowly at depth. Subsequent impacts mixed these materials, creating the heterogeneous samples that Chang'e 6 collected 4.25 billion years later. The iron signature that dominates South Pole Aitken Basin's spectroscopic appearance has puzzled scientists since its discovery. The basin floor shows elevated iron and titanium compared to surrounding highlands, yet volcanic plains cover only 8% of the basin's interior. Where does the iron signature come from? New analysis suggests the signature predated the basin. The lunar crust may have been stratified with respect to iron concentration. The upper crust contained less iron, the lower crust contained more. The South Pole Aitken impact excavated the iron-poor upper crust, piling it into the basin rim. It exposed the iron-rich lower crust on the basin floor. This stratification would have formed during primordial crust formation. As the magma ocean crystallized, plagioclase floated to form the crust. But plagioclase chemistry varied with depth. Early crystallization produced iron-poor plagioclase. Later crystallization from more evolved magma produced iron-richer plagioclase. The result, a compositionally layered crust. The South Pole Aitken impact sampled this stratification, revealing structure that would otherwise remain hidden. We're literally looking at the moon's geological cross-section, exposed by the violence of ancient collision. This stratified crust theory solves multiple puzzles simultaneously. Why does South Pole Aitken show elevated iron without extensive volcanic cover? The impact exposed deeper, iron-rich layers. Why do spectroscopic measurements show such stark compositional differences between basin floor and rim? They're sampling different crustal depths. Why has this signature persisted for over 4 billion years? It's not a surface coating that erosion could remove. It's the fundamental composition of exposed crustal layers. But crustal stratification raises its own questions. How did the primordial crust develop layered chemistry? The answer returns us to the magma ocean, that global molten shell that dominated the Moon's first 100 million years. As the magma ocean cooled, minerals crystallized in sequence based on their melting temperatures. Olivine and pyroxene formed first, sinking through the liquid. Plagioclase formed later, but it was less dense than the surrounding magma. It floated upward, accumulating at the surface to create the primordial crust. This process wasn't instantaneous. It took millions of years. During that time, the chemistry of the remaining magma evolved. Early plagioclasic crystals formed from relatively primitive magma. Later crystals formed from more evolved, iron-enriched liquid. The result: progressive chemical stratification within the growing crust. The deepest crustal layers contain plagioclase that crystallized early, when the magma ocean was hotter and less evolved chemically. The upper crustal layers contain plagioclase from later crystallization stages, incorporating more iron and other elements from the progressively enriched magma. South Pole Aitken excavated through this stratification. The impact punched deep enough to reach the iron-rich lower crust, exposing materials that had been buried since the Moon's formation. The excavated upper crust piled into the basin's rim, creating the elevated iron pore highlands that surround the depression. This is extraordinary. We're observing lunar formation processes directly, written in the composition of exposed rock layers. But there's a complication. Not all scientists agree that South Pole Aitken exposed only crust. Computer simulations suggest the impact should have penetrated much deeper. For a basin this size, formed by a projectile perhaps 200 kilometers across, models predict excavation depths reaching 200 kilometers below the surface. That would breach the crust entirely, excavating mantle material from depths where olivine and pyroxene dominate. Yet we don't see strong olivine signatures in South Pole Aitken spectroscopy. The basin floor shows elevated iron, yes, but the mineral assemblage still looks crustal. Crustal thickness maps from Grail confirm about 30 kilometers of crust beneath the basin floor, compared to 60 to 80 kilometers in surrounding regions. If the impact excavated 200 kilometers deep, where's the mantle material? Several explanations have been proposed. Perhaps the impact wasn't as deep as models predict. If the projectile struck at a shallow angle rather than vertically, it could have created a massive basin without penetrating to great depth. Low-angle impacts spread their energy laterally rather than driving downward. The basin's shape offers clues about impact trajectory. South Pole Aitken isn't perfectly circular. It tapers toward the south, and topographic transitions are more gradual in that direction. This asymmetry suggests a southward impact trajectory, with the projectile approaching from the north at an oblique angle. Oblique impacts don't excavate as deeply as vertical ones. Energy that would drive downward in a head-on collision instead gets redirected laterally, creating a large but relatively shallow crater. This could explain why South Pole Aitken is enormous in diameter but didn't breach the crust completely. Alternatively, maybe the impact did excavate mantle material, but that material isn't where we're looking. The most pristine ejecta from deep excavation wouldn't land on the basin floor. It would be thrown outward, deposited beyond the rim in rays and secondary crater fields. The basin floor, conversely, would contain a mixture of melted crust and debris that slumped back after the initial excavation. This might explain the crustal composition observed on the floor while still allowing for deep excavation. Recent mapping identified a thorium-rich deposit southwest of South Pole Aitken. Thorium concentrates in creep materials, those late-stage magma ocean liquids enriched in incompatible elements. Finding thorium-rich ejecta southwest of the basin suggests the impact excavated deep enough to reach pockets of residual K-reap that had accumulated at the base of the crust or top of the mantle. This K-reap signature points to partial excavation of late-stage magma ocean materials. The impact occurred during a critical window in lunar evolution, when the magma ocean had mostly solidified, but pockets of residual liquid still existed at depth. Timing matters here. South Pole Aitken formed 4.25 billion years ago. The Moon itself is 4.51 billion years old. That's a gap of only 260 million years. For geological timescales, that's rapid. The magma ocean may have taken 50 to 200 million years to crystallize completely. South Pole Aitken could have struck when crystallization was advanced but not entirely finished, when dense ilmenite cumulates were sinking through the mantle, and residual creep liquids were being squeezed into pockets between solid cumulate layers. Hitting the Moon during this transitional state would produce complex results. Some regions excavated would be fully solid cumulates. Others might tap residual liquid pockets. The resulting ejecta would show mixed signatures, exactly what we observe. This timeline also matters for understanding the lunar cataclysm hypothesis. For decades, scientists debated whether the inner solar system experienced a spike in impact rates around 3.9 billion years ago, called the Late Heavy Bombardment. Evidence came primarily from dating Apollo samples. Many rocks showed ages clustering around 3.9 billion years, interpreted as reset ages from major impacts during a bombardment spike. But South Pole Aitken predates this window by 350 million years. If the Moon's largest basin formed before the supposed bombardment, that challenges the cataclysm narrative. Recent analysis suggests the clustering of ages around 3.9 billion years might be observational bias. Apollo missions sampled limited regions, many near Imbrium Basin, which formed around 3.9 billion years ago. That basin's ejecta blanket covers vast areas of the near side. Many 3.9 billion-year-old samples might simply be Imbrium impact products. South Pole Aitken's age of 4.25 billion years provides crucial context. Major basin-forming impacts weren't confined to a narrow bombardment window. They occurred throughout the Moon's first billion years, with the rate declining over time as planetesimals were swept up or ejected from the inner solar system. The impact that created South Pole Aitken represents the tail end of planetary accretion. It struck when the Moon was geologically young but no longer molten. The impactor was probably one of the last large planetesimals in Earth-Moon space, its orbit eventually intersecting the Moon's, with catastrophic results. After the impact, South Pole Aitken became a topographic low, a massive depression that would influence lunar evolution for billions of years. Volcanic magma, when it eventually formed deep in the mantle, found easier pathways to the surface through the thinned crust beneath the basin. This explains the volcanic plains within South Pole Aitken, though they're limited. Magma preferentially erupted where the crust was thinnest. The basin's floor, with only 30 kilometers of crust instead of the typical 50 to 80 kilometers elsewhere, provided such pathways. But volcanism within South Pole Aitken was never as extensive as on the near side. Why? The answer connects to the crustal dichotomy we discussed earlier. The near side's thinner crust made volcanic eruptions easier. Heat-producing elements concentrated in the Procellarum creep terrain kept the near side mantle warmer longer, promoting prolonged volcanic activity. The far side, with its thicker crust and lack of creep enrichment, experienced less volcanism. Even within South Pole Aitken, where the crust was locally thinned by impact, volcanic activity remained muted compared to near-side Maria. Chang'e 6's volcanic samples tell this story. The basalts are ancient, 2.8 billion years old for most fragments. One fragment dates to 4.2 billion years, making it among the oldest lunar volcanic rocks ever sampled. These ages indicate that far-side volcanism occurred early and ceased relatively quickly. The mantle beneath the far side didn't stay hot enough to sustain prolonged melting. By 2 to 3 billion years ago, volcanic activity had essentially stopped. Contrast this with the near side, where volcanism continued sporadically until just 120 million years ago in some regions. The thermal evolution diverged dramatically between hemispheres. Space weathering adds another layer to the story. Samples from the lunar far side show different weathering characteristics than near-side materials. The Moon has no atmosphere and no magnetic field. Solar wind particles, cosmic rays, and micrometeorite impacts constantly bombard the surface, altering rock chemistry and texture over time. This process, called space weathering, affects all airless bodies, but Earth's magnetic field provides partial protection to the lunar near side. Once per month, as the Moon orbits Earth, the near side passes through Earth's magnetotail, a region where Earth's magnetic field extends downstream from the Sun. During this passage, the near side is shielded from solar wind. Particles that would normally impact the surface are deflected by Earth's magnetic field. This reduces weathering rates on the near side compared to the far side. The far side never enters Earth's magnetotail. It receives continuous solar wind bombardment month after month for billions of years. Chang'e 6 samples reflect this difference. Far-side samples lack certain vapor deposition layers found on near-side rocks. They show thinner amorphized rims on mineral grains. Solar flare track densities are lower. Nanophase metallic iron particles, which form from solar wind reduction of iron-bearing minerals, are larger but less numerous. These subtle differences reveal the environmental contrast between hemispheres. The Moon's two faces experience different space weather, leaving distinct signatures in surface materials. Understanding these weathering differences matters for future exploration. As humans return to the Moon, we'll need to account for environmental variations. Radiation exposure, dust behavior, resource extraction techniques all may differ between near and far sides. The far side, lacking Earth's protective magnetotail, presents harsher radiation conditions. Astronauts working there will need enhanced shielding. Equipment will face more intense weathering. But the far side also offers unique opportunities. Radio astronomy, for instance, could flourish on the lunar far side. Earth's radio noise, from television, radio, communications satellites, all the electromagnetic chatter of technological civilization, doesn't reach there. The Moon itself blocks it, creating a radio quiet zone unlike anywhere accessible in near-Earth space. Astronomers have long dreamed of placing radio telescopes on the far side. They could observe frequencies impossible to detect from Earth, studying the cosmic dark ages before the first stars formed. Mapping the universe's large-scale structure through 21-centimeter hydrogen emission, searching for faint signals from the early universe. Communication challenges delayed this dream for decades. Without relay satellites, far-side installations couldn't send data to Earth. Chang'e 4 solved this problem in 2019 with the Queqiao relay satellite, positioned at the Earth-Moon L2 Lagrange point, where it maintains constant line of sight with both Earth and the far side. This relay architecture enabled Chang'e 4's landing in Von Karman crater, within South Pole Aitken Basin. The Yutu-2 rover has operated there for over 5 years, studying far-side geology and testing technologies for future exploration. Artemis missions will continue this work. Proposed landing sites near the lunar South Pole sit on South Pole Aitken's rim, on ejecta deposits from the basin forming impact, Astronauts will walk on material thrown from depths of tens of kilometers, sampling the moon's ancient interior brought to the surface by violence 4 billion years ago. They'll collect rocks that may contain traces of the moon's mantle, brought up from depths we've never sampled before. These materials could answer fundamental questions about planetary formation. How do rocky worlds differentiate into core, mantle, and crust? What processes dominated the early solar system? The far side holds these answers, preserved in stone for 4 billion years. Future missions will expand this exploration. Chang'e 7, scheduled for launch in 2026, will survey the South Polar region for water ice and other resources. Where exactly does ice accumulate in permanently shadowed craters? How much is there? What form does it take? These questions matter not just for science, but for establishing sustained human presence. Water means life support, breathable oxygen, rocket fuel. Finding it on the moon changes everything about future exploration architecture. Chang'e 8, planned for 2028, will test resource utilization technologies. Can we extract oxygen from lunar regolith, manufacture building materials from local rock, 3D print structures using lunar dust? These experiments will demonstrate whether the moon can support permanent settlements, or whether every supply must come from Earth at enormous cost. The far side becomes a testing ground for technologies needed throughout the solar system. International collaboration drives these efforts forward. China has invited scientists worldwide to study Chang'e 6 samples. Research teams from Europe, America, Asia, and beyond are analyzing these materials, bringing diverse expertise to common questions. Professor Mahesh Anand from Britain's Open University noted that Chang'e 6 findings are turning many well-established hypotheses and theories in lunar science upside down. International cooperation accelerates discovery in ways no single nation could achieve alone. This collaboration model may define future exploration. Rather than competing space races, nations increasingly share data, coordinate missions, and pool resources. The Artemis Accords, signed by over 30 countries, establish principles for peaceful lunar exploration, transparency, interoperability, emergency assistance. These commitments create framework for sustainable exploration benefiting all humanity. The far side becomes common ground, literally and figuratively. Yet significant mysteries remain. That massive anomaly beneath South Pole Aitken Basin, what exactly is it? Grail data revealed its existence, a concentration of dense material 5 times larger than Hawaii's Big Island, dragging the basin floor down by more than half a mile. Is it the metallic core of the impactor that created the basin, still embedded in the moon's mantle, or something else entirely? The anomaly extends to depths exceeding 300 kilometers, far deeper than we can drill with current technology. Future geophysical surveys may reveal its true nature, but for now, it remains one of the moon's deepest secrets. The origin of the near-side-far side dichotomy also puzzles researchers. Why are the hemispheres so different? Several theories compete for acceptance. Perhaps 2 moons once orbited Earth and merged early in lunar history, adding extra crust to one side. Or maybe a large object, a dwarf planet perhaps, collided with the young moon at relatively low speed, depositing material that buried the far side's primordial surface. Grail detected that extra crustal thickness, 3 to 6 miles of additional material on the far side, but determining how it got there requires more data. Heat distribution may explain the volcanic asymmetry. The near side crystallized more slowly than the far side, potentially accumulating more heat-producing radioactive elements like potassium and thorium. These elements concentrated in the Procellarum creep terrain, that compositional anomaly covering much of the near side. Their radioactive decay would have lowered mantle melting temperatures, producing vastly more magma beneath the near side than the far side. Laboratory experiments support this mechanism, suggesting the near side mantle could generate 4 to 13 times more volcanic material. But the full story likely involves multiple factors working together in ways we're only beginning to understand. The timing of South Pole Aitken's formation remains debated. Different dating methods yield slightly different ages. Chinese scientists analyzing Chang'e 6 norites determined the basin formed 4.25 billion years ago. Other researchers, studying lunar meteorite Northwest Africa 2995, calculated ages between 4.32 and 4.33 billion years. These differences may reflect measurement uncertainties, or they may indicate we're dating different aspects of the impact event. The initial impact, the cooling of melt sheets, the final solidification of ejecta. Each process occurred at different times, potentially leaving distinct isotopic signatures. Understanding this timeline matters because South Pole Aitken formed during a pivotal epoch. The Moon's magma ocean was crystallizing, creating the layered interior structure we observe today. Heavy bombardment pummeled all inner solar system bodies, reshaping planetary surfaces, and possibly delivering water and organic compounds to Earth. South Pole Aitken's impact occurred at this critical juncture, potentially excavating late-stage magma ocean liquids and mixing them with impact melt. Chang'e 6 norites show evidence of exactly this process: crystallization from impact melt sheets containing materials from various depths. Each sample tells part of this violent story. The impact trajectory has been re-examined. Earlier models assumed a northward impact, but recent analysis suggests the opposite. The basin's outline tapers toward the south, and topographic transitions are more gradual in that direction. A southward trajectory would produce these features. It would also explain the thorium-rich, iron-rich ejecta deposit southwest of the basin, material from deep in the crust or shallow mantle, thrown downrange by the impact. This seemingly technical detail actually reveals fundamental aspects of how giant impacts reshape planetary bodies. Excavation depth remains uncertain. Simulations suggest near-vertical impacts should dig to 200 kilometers depth, potentially exposing mantle material. Yet observations don't clearly show mantle composition on the basin floor. Crustal thickness maps indicate about 10 kilometers of crust beneath the basin, less than the 50-kilometer global average, but still substantial. Perhaps the impact wasn't vertical. A low-angle impact by a 200-kilometer projectile hitting at 30 degrees or less would create the observed basin without penetrating as deeply. This scenario fits some data better than traditional high-velocity vertical impacts. These competing hypotheses illustrate how far-side exploration challenges our understanding. Every answer raises new questions. Every sample suggests alternative interpretations. This is science at its frontiers, where certainty gives way to probability, where models compete for explanatory power, where the next measurement might overturn decades of theory. The far side forces us to question assumptions, refine methods, embrace uncertainty as the path to knowledge. Human observers add unique value to this process. When Artemis II astronauts viewed the far side in April 2026, they spent 7 hours photographing and documenting surface features. Their observations included unexpected details: brown and green hues on the near side, smaller craters appearing unusually bright, like lampshade with tiny pinprick holes. As astronaut Koch described them, these subjective human observations complement robotic measurements, providing context and intuition machines cannot replicate. The astronauts also experienced something profound. During their far-side passage, they witnessed a solar eclipse from behind the Moon. totality lasting about an hour. They saw Mars, Venus, Saturn alongside stars, Earth's faint glow and wispy corona baby hairs at the lunar disk's edge. But more than visual spectacle, the experience changed them. Koch reflected that viewing Earth from lunar distance reminded the crew how much we have in common, that everything we need Earth provides, which is somewhat of a miracle. This perspective, seeing our world as others have, fragile and precious against the cosmic dark, may be exploration's most valuable product. 24 humans have seen the far side directly. The Apollo crews who orbited the moon between 1968 and 1972, and now the Artemis II astronauts. Each described it differently. William Anders called it a sandpile kids have played in for some time, all beat up with no definition, just bumps and holes. Others found beauty in the desolation, meaning in the ancient cratered highlands. These varied responses reflect how exploration is ultimately a human endeavor, filtered through individual perception and experience. Yet for decades, far-side exploration seemed impossible. Harrison Schmitt, geologist, astronaut, and last person to walk on the moon, lobbied aggressively for Apollo 17 to land in Tsiolkovsky crater on the far side. His ambitious plan included a relay satellite at the L2 Lagrange point to maintain communications during descent and surface operations. NASA rejected the proposal as too risky, too expensive. The far side remained tantalizingly out of reach, visible but inaccessible, known but unexplored. Technology eventually solved the communication problem. China's Queqiao relay satellite, launched in 2018 and positioned at Earth-Moon L2, provides continuous line of sight between Earth and the far side. This architecture enabled Chang'e 4's landing in Von Karman crater, where the Yutu-2 rover has operated for over 5 years, studying far-side geology and demonstrating long-duration surface operations. Queqiao proved the relay concept works, paving the way for future missions. The far side offers advantages beyond geology. Radio astronomers have long dreamed of placing telescopes there, shielded from Earth's electromagnetic interference by the moon itself. Every radio transmission, every television broadcast, every satellite communication creates noise that obscures faint cosmic signals. The far side experiences none of this. It's the quietest radio environment accessible to humanity, perfect for observing frequencies impossible to detect from Earth. What could we discover with far-side radio telescopes? They could study the cosmic dark ages before the first stars formed, mapping the universe through neutral hydrogen emission. They could detect gravitational wave backgrounds from the early universe, signals too faint for Earth-based instruments. They could search for technosignatures, evidence of other technological civilizations, broadcasting across interstellar distances. The far side becomes a window on cosmos we've never clearly seen. These possibilities drive current planning. Future missions will scout locations for radio telescope arrays, test deployment technologies, demonstrate science operations in the far side environment. The moon transitions from destination to platform, from place to visit into place to work, to build, to establish permanent presence. The far side, once the most remote location humans could imagine, becomes the next frontier. This transformation reflects broader patterns in exploration history. Remote regions, polar ice caps, ocean depths, mountain summits follow similar trajectories. First contact and mapping, then scientific expeditions retrieving samples. Eventually sustained presence, permanent stations, regular operations. The far side has entered this middle phase between initial reconnaissance and full utilization. What comes next depends on choices we make today. Resource questions loom large. Water ice in polar cold traps could support human crews and fuel spacecraft. Rare earth elements in impact ejector might enable local manufacturing. Solar power in regions receiving near-constant sunlight could provide energy for expanding operations. The far side isn't just scientifically interesting, it's potentially useful in ways that justify the enormous costs of lunar exploration. But utility shouldn't overshadow wonder. The far side remains one of the strangest, most ancient, most scientifically valuable places humans can reach. Every rock tells billion-year stories. Every crater preserves solar system history. Every sample contains clues about planetary formation, cosmic bombardment, the processes that made rocky worlds possible. Understanding the far side means understanding how Earth itself came to be. We stand at a remarkable moment. Robotic explorers have returned far side samples for the first time. Human crews have viewed the entire lunar far side directly. Future missions will land astronauts on South Pole Aitken's rim, walking on material from the Moon's deepest interior. International collaboration expands access and accelerates discovery. Technologies mature that enable sustained presence. The far side, hidden for all of human history until 1959, now reveals itself through an unprecedented convergence of capability and curiosity. What we learn there will shape humanity's relationship with the cosmos for generations to come. The far side isn't finished telling its story. Every sample analyzed reveals something unexpected. Every measurement challenges previous assumptions. The Chang'e 6 materials continue yielding discoveries that force scientists to reconsider theories built over decades. Professor Anand wasn't exaggerating when he said these findings are turning lunar science upside down. The 4.2 billion-year-old basalt fragment alone extends volcanic history by over 1 billion years beyond what models predicted. The norites crystallized from impact melt containing meteoritic metals proved the South Pole Aitken collision was even more violent and complex than simulations suggested. The space-weathering differences between hemispheres demonstrate that even processes we thought we understood operate differently than expected. This pattern will continue. Future missions will return more samples from different locations within the basin. Each new site samples different depths of excavation, different impact melt compositions, different volcanic episodes. The South Pole Aitken Basin is so vast that we could conduct 100 sample return missions and still not fully characterize its diversity. Every rock tells a different part of the story. Every measurement adds another constraint to our models. The Artemis program will accelerate this process. When astronauts land on the basin's rim in coming years, they'll collect samples that no robotic mission could reach. They'll make field observations that cameras cannot capture. They'll recognize context that matters for interpreting laboratory measurements back on Earth. Human exploration and robotic sample return complement each other, each enabling discoveries the other cannot achieve alone. But the far side's significance extends beyond lunar science. It's teaching us how to explore other worlds. The techniques developed for far-side communications work anywhere line of sight to Earth is blocked. The resource utilization technologies being tested will be needed on Mars, on asteroids, throughout the solar system. The international collaboration frameworks prove that peaceful cooperation can overcome technical and political obstacles. The far side becomes a proving ground for humanity's expansion into space. Those mass anomalies beneath impact basins likely exist on other worlds too. Mercury, Mars, even Earth probably harbour similar buried structures from ancient collisions. Understanding what South Pole Aitken's anomaly actually is will help us interpret similar features elsewhere. Is it metallic impactor material? Dense mantle cumulates? Some combination we haven't considered? The answer matters for planetary science broadly, not just lunar studies. The volcanic history revealed by Chang'e 6 samples challenges our understanding of how rocky worlds cool and evolve. If the far side remained volcanically active billions longer than expected, what does that imply for other planets? Mars shows ancient volcanic plains, but also relatively young lava flows. Mercury has volcanic features that don't fit simple thermal evolution models. The Moon's two hemispheres followed different thermal trajectories, despite being part of the same body. This complexity may be normal, not exceptional. Space weathering differences between near and far sides matter for interpreting remote sensing data from asteroids, Mercury, Mars. Any airless body where solar wind bombardment shapes surface properties. We can't assume weathering rates are uniform. We have to account for magnetic field protection, orbital geometry, solar distance. The Moon teaches us what to look for elsewhere. These lessons accumulate slowly. Decades of lunar exploration have revealed how little we actually understood despite centuries of telescopic observation.